Okay, in this video I'm going to talk about study design and the different types of study and how much you can hang your hat on each different kind of study. So first, what is epidemiology? It's pretty simple. Epidemiology is the study of the health of a population. So what is health? Is it the slowest way to die? Is it the happiest life? So that's kind of a contention, and each person may have their own definition. So instead of debating on what health is, we're just going to say we study health, and what's the purpose of it? We want to find out what causes or what risk factors are associated with, or what the prognosis and best treatment is for various diseases. So for example, a recent study would ask the question, should we hospitalize patients with pneumonia? And the study pointed out that some people were treated in the hospital, other people were treated at home. They were randomized on who would get the different treatments, and it turned out that the people who were treated at home had an equally effective treatment as those who were treated in the hospital. So contrary to popular or older beliefs that you have to treat pneumonia in the hospital, it's not really the case. You can treat it at home. And that's just some of the kind of questions that epidemiology seeks to answer. So that would be like a what's the best treatment kind of question. A question asking about risk factors may ask something, for example, like if a 75-year-old man with hemoptysis and shortness of breath, he had an x-ray showing that the apical lung had a mass. He worked as a miner for 30 years. So because of epidemiology, we know that this man probably has silicosis. And basically what that means is studies of risk factors of silicosis have pointed out that people who work as a miner for long periods of time, that's a risk factor, and that studies of the causation, studies of the various diagnostic tests show that whenever you are a miner and you have an apical lung mass, you're even higher risk that lung mass is silicosis. Okay, without further ado, let's talk about study types. I'm going to go over all the main study types quickly, and then I'll hit a few others in subsequent videos. The first is called a case series or a case study. So a case study would say, hey, this person came into the clinic, he had really interesting presentation. I'm going to write up some things to describe this person and this disease. So it's basically is usually just one person or one case. And then whereas a case series is where you have multiple cases that are very similar. So basically you identify a person with a disease or condition of interest, you get information from those people, and then you describe the person or people with the disease. Do they have something in common? You do not compare in a case study. Usually there is no comparison to a control group. You're simply just looking at the person who has the disease. What can a case study not tell you? It cannot tell you what causes the disease. It cannot tell you what will happen to all or even most people with the disease. It cannot tell you what factors are associated with it. It can't tell you how common it is. It can't even tell you what the best treatment is. The exception to this rule, the best treatment, whenever you're talking about case studies, they're called parachutes or all or nothing. So if you do something to all people and they always get better rather than the nothing that we had before, and the example of this is an appendectomy. Before, a lot of people with appendectomies would die, people with appendicitis would die, rather. And then when they started doing appendectomies, everybody got better. And so you really didn't need to go beyond a case study or a case series to show that appendectomy was a great treatment. And likewise, you really don't, you talk about if this person jumped out of a plane, he had a parachute on, he survived. It beats everybody else that died without the parachute. You don't really need to do a comparison study whenever everybody who jumps out of the plane with the parachute survives. The next kind of study is a cross-sectional study. Think of this as a cross-section through time and space. So you pick your particular place of interest, and you do in a single time, you do a study. The study really doesn't look that far backwards into time. It doesn't follow people forwards into time. It's just, I want to look at this disease and these people right now. Another way to think of it is basically like a census. Who does and does not have the disease. And so it can tell you, if you do this right, you can find out the prevalence of the disease. You can find out what conditions are associated with it. So you say, let's say everybody in the med school class, I'm going to interview all of them and find out which of them fall asleep during lecture. When you're done interviewing this class of 9 people, you'll find out that the prevalence is 3/9. So 3 of the 9, or 1/3, 33% of the people have this condition of falling asleep during lecture. You may also ask questions about who drinks coffee, who stayed up late, and you can find out what conditions are associated with it, but you can't find out what causes it. One of the problems with this is it doesn't tell the incidence, so I can find out everybody at this time who has the disease. That's the prevalence. But you won't know who's going to have the disease tomorrow or the condition tomorrow. You won't know if the condition gets better or stays as permanent, as chronic. You don't know what happens to the people with the condition. You don't know about how many more people are going to get the condition. You don't know what causes it. You don't even know the best way to treat it. Another kind of study is called a case-control study, and so this is good for rare diseases. In our case, we're going to look at the sleeping students in class. Suppose that the lecturer stands right here, and he gives his boring lecture to the class, and then you say to yourself, I'm going to find a random selection, or I'm going to take some cases, which I'm going to pick 2 of the cases, or I'll just take all 3 of the cases, and then I'm going to take 3 controls. Usually you want your controls to match your cases on everything that is important, so maybe height, weight, the amount they stayed up at night, that kind of thing. Maybe those things are not important to what you're looking for in the disease. Maybe you're looking at coffee drinking, and so you would want them to be similar on everything except coffee drinking. And you don't go and say, oh, you drink coffee, or you drink coffee and you don't. You just say, I want you to be similar on as much as possible, and then I'm going to see if you're similar on the things that I think are important. So in a case control study, you start with cases. Cases and controls. So the cases are people with a disease or with a condition. It is not an exposure status. We don't know what they are exposed to yet. We're trying to figure out what exposures cause this disease. So cases are people with disease. Exposure status doesn't matter. Controls are people without disease. No disease. So as I've written here, you identify a group of people with the disease, you find another group of people without the disease, then you look backwards towards exposures and you compare differences. And then you'll use an odds ratio. So remember, with a case control study, you cannot use risk or relative risk. You have to use odds ratio, because with a case control study, you do not get important information such as incidence. Incidence is needed in order to measure risk and relative risk. And we'll talk more about the math behind it in an upcoming video. But for right now, I'll just show you. What you would do is you'll make a 4x4 box. And these are cases. These are controls. Then you'll look back into time and you'll say, okay, I need to find out what happened to what caused this. And so the first thing you might think of is that the people that are cases stayed up late, and so you interview them. They stayed up late, they went to sleep early. And you find out that 2 of the cases were up late, 1 of the controls, 1 of the cases went to bed early, and 2 of the controls did. So when you do your odds ratio, you'll find that the odds ratio is 4. 4 is a fairly good odds ratio, and so you have a you're 4 times more likely to fall asleep if you stayed up late than if you went to bed early. And I'll show you how to calculate these later. So, like I said, it can show you what factors are associated with a condition. So staying up late is associated with this condition. It does not necessarily mean that it causes it, but it's something that you can investigate further now. Problems with it, like I said, it cannot say what causes it. It's not good for rare exposures. It doesn't tell you what the best treatment. You don't know the prevalence. You don't know the incidence. So in this example, basically what I'm saying, I don't know the prevalence or the incidence. All I did was come in and I selected three cases, and then I found 3 more controls to compare them to. I don't know how many other people are in this population, and I don't know how many other people are going to get this disease or how often the disease presents, so I don't know prevalence or incidence. Case control studies are highly susceptible to confounding, and so the classic example of that is, does coffee cause pancreatic cancer? So a case control study looked at people that had pancreatic cancer, and they said, okay, now let's see if we can find any common exposures. And a lot of people who had pancreatic cancer were also coffee drinkers. So it was found that drinking coffee is associated with pancreatic cancer. So does it cause pancreatic cancer? And the clear answer right now is no, it does not. So why did this association pop up? Well, it turns out that smoking cigarettes is also associated with drinking coffee. Smoking cigarettes does cause pancreatic cancer. And so because this third variable, smoking, is associated with both the disease and this other confounder, it looks like coffee may be causing pancreatic cancer. And for a short time they thought maybe that was the case, until they discovered that it was actually cigarette smoking that was associated with both. Now it's important to remember that case control studies are susceptible to confounding. All kinds of studies are susceptible to confounding, but case controls are the ones you really have to be careful with confounding. The next one's a cohort study, and the way I'm going to explain that is we're going to say that we have an exposure to some incidents, and then we're going to have people that did not get the exposure. Let me change the color on that. So people that did not get the exposure, and then we have people that did get some kind of exposure. Let's say it's to radiation. So I find a group of 5 people that were exposed to radiation, and I find a group of 5 people that were not exposed to radiation, and I decide to follow them forward into time and to see what diseases each group gets. And so we know that out of the 4 of the 5 that were exposed to radiation, they all got cancer, and then 1 of them died of automobile accident. And then out of these others that were not exposed to radiation, we had 2 die of dog bites, we had 1 die from drowning, and we had 1 die from cancer. In both cases, so the 4 that died from cancer, they died fairly early, whereas all of these that died late, they died later on, much later on. So we had early deaths versus late deaths, and so we can say that's part of the exposure versus the non-exposure. And if you get a large enough group of cohorts, so a cohort, you start with the exposure, you get those that are exposed and those that are not exposed, and you follow them forward in time until you find a disease of interest. So the disease is unknown and the exposure is known. So it's the exact opposite of the case control. In the case control, you start with the disease and you go back towards exposure. In the cohort, you start with an exposure and you follow these people for long periods of time. So let's read. Identify and follow people with a specific exposure. Identify and follow another group without that exposure. See what happens to people in both groups. So it can tell you how common a disease is. It can tell you what happens to people with that disease. It can tell you factors that predict a disease. It also tells you the incidence and prevalence of a disease. So all of those things that we weren't getting in the other studies, we can get with a cohort study. A few things it doesn't do well with: it cannot tell you what the best treatment is, and it's not good for rare diseases, but it is good for rare exposures. For example, there's the atomic bomb survivor cohort study, where people that survived the atomic bombs in Nagasaki and Hiroshima, for example, were followed to see what kind of diseases they would have and what kind of birth defects their children would have, and they were compared to control groups who did not have that atomic bomb exposure. One other thing you should know about cohort studies is that there are two kinds. You have a prospective, which is basically what I just described. That's where you start with an exposure, you follow the people for long periods of time. Then you have the retrospective. Retrospective is basically where you're going to look backwards in time, and you're still going to get all of the same information. So for example, you can do a retrospective study by looking at everybody who got an X-ray in a hospital. So an X-ray would be an exposure. You're not starting with a disease. You're starting with an exposure, and then you find a group of people that have had no X-ray. And then you go and you find those people and you interview them and you find out, do they have any specific diseases? And then you've already let the time run its course. You don't have to follow them for a long period of time. You've already let the time run its course. You can run tests on them, you can ask them questions, you can see what they have died from or what they've been sick from over the years by looking at their hospital and clinic records. So you don't have to spend as much money, but you do have some problems with this retrospective study. For example, how do you determine what X-rays, what amount of radiation exposure a person received? It might have been different for different X-ray machines. The equipment might have been different. And so there's a lot of things that could be different from one patient to the next, where their exposure isn't the same, where measurements and diagnostic tests weren't performed the same, and so you have less control. So we'll just say less control and leave it at that. So this is the last of what I would call a true study. And it's like the gold standard of true studies. This is the randomized controlled clinical trial, or RCT. This is great for, you can do two things. You can determine what causes a disease. That isn't necessarily ethical. So if it's not ethical, don't do it. But you can also determine the best treatment for a disease. So what does it do? You take a group of people, then you randomly assign some to a specific exposure and others to a control group. And so that exposure, usually in clinical-based trials, is a specific kind of medication. And the control group, it can be one of two things. It can be a placebo. It can be a placebo, or it can be the standard of care. Usually SOC, standard of care. So I want to see, does this new medicine work better than the old medicine at treating a disease? And so you compare this new medicine or this exposure to a control group, which is the standard of care. This costs a lot of money, a lot of time. You have to have access to the right people, so there's a lot of problems with it, but you can use it to determine the best treatment. Now, oftentimes, these kinds of studies will use subgroup analysis. So if a medication that you're using, if it doesn't perform better overall than the standard medication, then you might break it down and say between ages 14 and 22, from 23 to 45, and from 46 through older. You might say, oh, in this group it worked better, in this group it worked the same, in this group it worked worse. And so you have these subgroup analysis. They can be helpful and they can also be misleading. And they're misleading often because of something we'll talk about later on when we talk about multiple analysis. And the basic of it is, if you do multiple analysis, just by random chance, you're going to find something that's significant. even if it's just random. It doesn't really exist in the population, but by random chance you got a few people where it did work better, and so multiple comparison, multiple analysis can often be misleading, and sometimes they can be helpful. You can think of a randomized controlled trial as a type of cohort study. The difference is the experimenter controls who gets the exposure and who is assigned to the exposure is done randomly. So scratch this out. The experimenter doesn't really control who gets exposed to something. He controls who's admitted to the study, and then once people are admitted to the study, they randomly are assigned to an exposure or to a control group. And so that makes it different than a pure cohort study, which nature decides who gets the exposure, and sometimes the individual decides who gets the exposure. Now, up a level from all of these are things that are not really studies in the classical sense, but they are studies. So one is a systematic review, and this is basically like if there's 18,000 papers written on the best treatment for sleeping during class, for example. A systematic review will say paper A found X, and paper B found Y, and paper C described symptom Z. And so it's a systematic way of taking all of these papers and getting them down into one little article. So these systematic reviews, they're a great way of getting a lot of information in a little bit of time. And the gold standard for these are the Cochrane reviews. Cochrane is the place that does excellent systematic reviews looking at multiple different studies of multiple different kinds, even analyzing how good those studies are, or how good the study designs are. And they'll say, this study was done, but the study design sucked. This study was done and found different results, and the study design was impeccable. We, for this reason, think that study number 2 has more weight than study number 1, and they give really good detailed reasoning. You can combine a systematic review into a meta-analysis, which I'm going to talk about next, but there are some distinct differences. So, in short, you can think of a meta-analysis as a systematic review that combines all of the data and reanalyzes all of the statistics, which that's what it does. But it's slightly different than a systematic review in that we're not describing paper A found this, paper B found that, paper C found this. A meta-analysis will say paper A used 20 people, and of those 20 people, 18 had X condition, and paper B had 45 people who had, of those, 42 had X condition, and then it'll add all of these up, find new averages, find new statistical significances. So a meta-analysis will combine data from several studies, and it will allow for a true estimate of effect size. The difference between a meta-analysis and a systematic review is that it uses the numbers, it uses the exact data to do new statistics. A systematic review will simply redescribe all of the old data, whereas a meta-analysis will take all of that old data to come up with new statistics. The advantage of this, like I said, you can find the effect size, you can control for study variation. So study A might have been done a little bit different than study B and a little bit different than study C. And so by combining all of these studies and reanalyzing their stats, you can control for that variation. It deals with information overload. It has less influence of local findings. And so a lot of times now you'll see studies that are done in multi-hospital locations. And the reason they do that is because each hospital is going to have slight variations in how well they perform and how they treat patients and how fast they get from point A to point B. And when you do a multi-site study, you control for all of those variations. And so a meta-analysis is one way of getting multi-site information into one study. It also can show publication bias when they exist. So typically a journals only like to publish findings when there are true findings. If you say, we did this study and we found that there is no difference, so no difference between A and B, then journals don't like to publish null findings. That's what they call a null finding. And whenever you do a meta-analysis, the statistics can show if there's a publication bias or not. And so that's one advantage of it. The disadvantages are junk in, junk out, so you can't fix how data was collected in the individual studies. If they were collected poorly, you can't fix that. You rely on published studies, so studies that were not published you can't use, and that's called the file drawer problem. Then you have Simpson's paradox. What do you do when studies go in two directions? And the example of this is cholesterol in eggs. This is the classic example. So in the 1980s, all eggs were bad because of cholesterol. And then in the 1990s, no, just the egg yolk is bad. The egg white is good. And then once you get to the late 90s, early 2000s, no, the whole egg is good. Just eat the whole egg. And why? Because 95 to 96% of our cholesterol comes from within our liver. Our liver produces cholesterol from HMG-CoA reductase. So even if you ate a crap ton of eggs, it would pale in comparison to the amount of cholesterol your body's actually going to make anyways. So that's kind of some of the reasoning. The cholesterol in eggs. So what do you do if you say, well, I want to know if cholesterol in eggs are really bad? And you look at the study that show cholesterol from eggs is bad. Then you look at the study that show that cholesterol from eggs is not bad. Well, you have problems with the studies going in two different directions. And so sometimes that's impossible to tease out with a meta-analysis. There was one other study type that I didn't mention that just needs brief mentioning because I'll cover it again later, and that's the ecological study type. It's basically where you take census level data and you compare it amongst countries. So one of them is a study of basically the age that somebody dies, death age, and income. And I think the actual variable is childhood mortality versus income, and you find that this country A, country B, country C, country D, the United States is somewhere in here, you got Dubai somewhere around here, and you can draw a clear line that as income increases, the mortality rate, the infant mortality rate decreases. But you can't, so the problem with this is called the ecological fallacy. Because you're taking population-based information instead of individual-based information, you cannot say that that because you live in this country, you will have a child of mortality. Or you can't also say, even though you live in this country, because you have a low income, your child will have a high mortality. You can't say anything about whether income causes or affects mortality. You can just say that it's related somehow. And I'll go more into the ecological fallacy in a future video. The thing you need to know about it is that it uses census or population level data and not individual level data. And it's one of the lowest, so you would put an ecological study near a case series or a case control, maybe just above it in its level of evidence. So speaking of evidence, let's say we have evidence over here. Which kinds of studies give you the best evidence? And so then we have study type. We would say low evidence would be like case control or not case control, but case series. And then you would have ecological. And then you would have cross-sectional. Then you would look at a case control. Then a cohort. And then finally a randomized controlled trial. And these are all the classical studies. Then above that you could put, depending on what was used, you could use a systematic review, and you could use a meta-analysis as the gold standard for evidence, especially if the meta-analysis were looking at multiple randomized controlled trials, and especially if the systematic review were looking at multiple randomized controlled trials. That would put these at the gold standard for evidence.